Okay, so now that that diversion is over, we can get back to proving sub-additivity. So again, just to recap what we've said so far, we're taking any countable collection of sets of real numbers, and we've already said that we will take for each fixed j, index j on the set of real numbers, a family indexed by k of open bounded intervals, right, open interval cover of that a sub j. And by definition of the infimum, if you bump it up a little bit, then there's some element, right, some overestimate contained within the set, which is less than that quantity. Now, the idea is you cobble together, right, so you take all the I sub j k's, right, and you cobble them all together, right, you know, for each j you get a collection of k, so you just union them all together. That's this right here, and we want to argue that this is a countable open interval cover of the entire union, and argue that the well, put it this way: the m star on that union, simply by definition of m star, right? That will make the sum over their lengths an overestimate. So right, so right, but so the point is that this inequality holds because this is a lower bound in the set of overestimates, and this is an overestimate. So anyway, okay, so the fact that this subset relation holds is just utterly trivial, right? Take any element out of this union, it must be contained in some a sub j. Now, this is an open interval cover of a, right, like, so it has some open interval cover for that corresponding j. And so since that's a cover, then that the element that you picked must be in one of these I sub jk's, and so since it's in one of these I sub jk's, it's therefore in the union. So this subset relation is very easy to argue. This is a countable union of countable sets, and therefore is countable, so there's no problem there. Here's where we needed the lemma, which is, well, okay, we're arguing that it's countable and we need to sum over this. Well, that really means that we index it by something and sum all the lengths according to that index, right? So we enumerate the set of all of these lengths coming out of this union, and we want to argue that the sum over all of those lengths, right, which we're calling b sub I here, is less than or equal to this quantity. So, we know this by definition. We have this by the theorem that or the lemma that we just proved. Now, if you just compute the sum over k in isolation, we know that term by term you can increase it by this. Performing the sum here, it just distributes. This is the geometric series and turns into just 1, so you're left with epsilon. And there's the proof, right? Like, you know, since this is true for any arbitrarily small choice of epsilon, then in general, m star of the union is less than or equal to the sum over the individual m stars. Therefore, m star is countably sub-additive. Okay, so the bad news is that m star is not countably additive. Now, it's not good enough to just prove that, because you know, there were several decisions that we made along the way, and you could always wonder whether or not we could have made different decisions to, you know, get some function which is, you know, defined on the power set of the real numbers, and you know, has all those other properties like getting intervals right and is translation invariant and so on, and maybe you would get something that's countably additive. And so what we're going to do is give a proof that no such function, right? There cannot be any function like that which satisfies those properties. And this is into, you know, especially the countably additive part is the part that, we really require if anything is going to be called any kind of a measure, right? I mean, these two properties are specific to the real numbers, and so the domain is specific to the real numbers, but when we go on to generalize the notion of measure, anything that we call measure is countably additive. So anyway, since the proof of this fact is not easy, then I'm going to start with a proof outline and try to make it as sensible as possible from a high level before going into the details. Okay, so the outline for the proof is that we will try to take the points, right? We're going to primarily work in the interval from 0 to 1, and we're going to try to sort of partition this interval into several different sets such that basically we measure each particular one, right? Measure them one by one, and because putting them all together will assemble back to the entire interval. The measure of the interval is going to have to be at least as big as the sum over all of the pieces. But either the pieces are going to have size 0 or size some finite number. But if the size is a finite number, then they will all have the same size, and therefore the sum over all of them will go to infinity. So basically, right, like I'm being very sort of unclear in my description there, but hopefully that gives some small amount of intuition. Now I'll talk about it in a little bit more detail, still not getting into the proof. But so the idea here, right, to begin with, is again on the interval from 0 to 1, we're going to find a way of selecting out points throughout this interval such that it's going to have a bunch of points, right? It's going to be dense in the interval, but it is also going to have a lot of gaps as well, right? So for that reason, right, I just kind of mentally visualize it as being like a feather. So I'm going to call this thing a feather, right? So we're going to construct this first feather. Then what we're going to do is we're going to take this feather and we're going to make copies of it, namely by translating this feather around, right? So we're going to get other feathers by taking this one and simply sliding it left and right and so on, in that way generating a whole bunch of copies of this feather. There will be countably many of these copies. We will only slide them around left and right by about plus minus 1, right, within that range. The idea being that by doing so, when we make a slight translation and have another feather just slightly offset, it'll cover extra points. And then you translate it a little bit more, and right, all these points will fit into the grooves in between all of the other points. So that by making all of these copies, we kind of fill back in the interval between 0 and 1 with all of these copies of feathers, right? And if we translate it to the left by 1, that is to say move, subtract 1 from all the points, then you're kind of sliding it all the way over here and filling in some of the gaps over here. But if you slide it just a little bit, you fill in other gaps, and if you slide it to the left, you fill in gaps over here, and so on. And so we never slide it more than plus or minus 1. Each slide is filling in little places throughout the interval with other feathers. Certainly there will be, right, like most of the feathers will have points that are outside this interval, but that won't matter too much because it will stay bounded between -1 and 2, right? So, so there will be countably many feathers. They will all be translations of each other, so they all have the same size by the principle of translation invariance. There will be a countable collection, and we will construct them in such a way that they will be disjoint from each other. So, right, once we get this collection of feathers, then we're ready to get started on the proof. So what we're going to argue is that the measure of the interval from 0 to 1, we know to be equal to 1. because we will have proved that the union over all of these feathers contains the interval from 0 to 1, then we get this by monotonicity, right? We get this by sub-additivity. We get this because they are all the same measure, so let's just call whatever its measure the number c. We know that this stays within the interval from -1 to 2, so the measure cannot be infinite, basically, right? It's going to, right, the union over all of the feathers is going to be a subset of -1 to 2, and that has measure 3. Therefore, again, by monotonicity, this sum has to stay finite. I'll argue that a little bit clearer later on, but basically by that kind of reasoning, because it stays within -1 to 2, this sum is going to stay finite. But if you are summing a constant infinitely many times and it stays finite, especially because these are non-negative numbers, then the constant must be 0. 0 is the only number that you can sum infinitely many times and still have a finite number, if it's constant. So, okay, so there you have it. We now know that c is equal to 0, therefore the sum over c is just the sum over 0, and that's equal to 0. And this, as we said, is greater than or equal to m star of 0 to 1, which is equal to 1. So it's a contradiction, right? You get that 1 is less than or equal to 0. So it's a proof by contradiction, right? We assume that a function like m exists, and we reach a contradiction. Okay, so we start the proof of the claim that there is no length measure, right? By this I mean that there is no function with this as its domain, satisfying all those properties of getting intervals right, and translation, invariance, and countably additive. So, as I discussed, we're going to construct a first feather, so is the word that I've made up for it. And we're going to get that feather by defining an equivalence relation that will partition the interval from 0 to 1. And the equivalence relation will be that any two numbers are related to each other if their difference is a rational number. Now, you know, it's easy to show that this is an equivalence relation. All you have to do is show reflexivity, which is trivial. That's just 0 in the rationals, okay? You have to show symmetry, but that's obvious, right? Because if that's irrational, then its negative is irrational. And transitivity, which I won't get into, but it's not hard at all. And so it's an equivalence relation and partitions the interval from 0 to 1. Now, I do want to point out, you know, like, why would you think that this equivalence relation and its associated partition are good ideas for this problem? You know, why try to investigate this problem this way? Well, you know, notice that one of the cells of the partition is the set of all rational numbers, right? You know, and that is a dense subset of 0 to 1. So there just is this feeling that that is kind of a, you know, it's dense. It like kind of feels like it covers everything pretty well, even if its cardinality is very small relative to the interval. It just seems, it's like, so to speak, everywhere in there, right? So that it almost feels like a sort of minimal copy of the interval. But there are also all of these other cells that are basically kind of just like it. So for instance, consider another cell of the partition, which is, you know, just to kind of like denote it by something. Let's say the cell that contains root 2 over 2, right? Root 2 over 2 is a number that's less than 1. And so it, right, there's a cell that contains it. And I just want to point out with an argument kind of like this, that, you know, it contains infinitely many other elements, right? I mean, you know, the solution to this equation is in the same cell, somewhat trivially, although, I mean, you would have to check that, you know, y is not too big or too small, but I'm pretty sure I've chosen this number small enough that they're close together, and that's not a worry. So there's this element, and then you know you could divide by 1,000 or 10,000 or so on and get this, you know, countable infinity, and that's not the only collection of elements in this cell. So anyway, I just want to point out that these cells, each cell contains a countable collection of elements. They're spread throughout the interval from 0 to 1. You know, this cell, by the way, does not just like, you know, this one contains all rational elements. Don't think that that means this one contains all irrational elements, because it will not contain pi over 4. So there will be an infinity of cells, and each one will contain an infinity of points. So that's kind of you know, something that you'd want to look at, because it feels like you're kind of getting infinitely many things that almost fill up the interval, and so by sort of spreading them out, translating them, and so on, you might be able to kind of get this infinite sum that we've discussed a little bit before. So that is kind of our starting place. So anyway, but to be clear, I have not yet told you what the feather is, right? All of this is in order to try to get the feather, but the partition and the cells and so on, none of those are the things that I have been calling the feather. So we have yet to see what that feather is, but we can do that right now. Okay, to get started, let lambda be an indexing set that enumerates the cells of the partition. So to put that more clearly, for each cell in the partition, we associate it with a unique lambda. So we will write every cell in the partition as some c sub lambda, where little lambda comes from big lambda. Now, that gives us a way of talking about the cells of the partition. Now, let's say that in each one of those cells, we pick a particular representative, right? Pick any element that's in the cell, call it little c sub lambda. Now we define the feather, the first feather, to be the set of all of those representatives, right? So this feather will have one rational number and one number which is related to root 2 over 2 by this relation, and one number related to pi over 4 by this relation, and so on. So it's the set of all of the cell representatives. Now, we're going to get all of the other feathers by considering an enumeration of the interval from -1 to 1, and then translating f by every possible element of that enumeration. Okay, so let's get an enumeration of the rationals between -1 and 1. This will allow me to construct all the other feathers, right? I'm going to use these rational numbers to translate the first feather in order to generate all of the other feathers. So that is to say, I'm getting an enumeration of this set here, the rationals between -1 and 1. And when I talk about the feathers plural, I'm talking about all of these, each r sub k plus f for some k. Now, I want to prove that the interval between 0 and 1 is contained within the union over all of the feathers. This is going to guarantee for me that the measure of this interval, which we know to be 1, is less than or equal to the measure of this union. So that we saw that was an important part of the contradiction that I'm building up. By the way, notice that we haven't actually proved monotonicity for this m that we are talking about in this proof, right? This is a general m. We proved monotonicity for m star from its definition as, you know, the infimum over estimates and so on. So we actually don't know yet that m is monotonic, but we will prove it eventually. For now, though, I'm just going to focus on getting this so that I'm ready to use monotonicity once I have it. By a similar kind of idea, I want to show that the union over all the feathers is contained within this set. That'll just make sure that when I use, when I take the sum, I will know that the sum cannot be bigger than the measure of this set, which is 3. I also want to use, I want to show that the feathers are each disjoint from each other. And that's going to be necessary for countable additivity. Recall that we don't know, right, or we haven't proved sub-additivity for this function. And we could, but it's just a waste of time. We just need additivity, so we'll just show that, you know, this meets the additivity constraint, right? Recall that when you're using additivity, you need to know that the sets are disjoint in order to use additivity. As a note, by the way, when I do get to proving disjointness, I will prove the converse, right? So this says that a set is disjoint when for every j not equal to k, the set indexed by j and k have intersection the empty set. I'm going to argue the converse. I'm going to suppose that this intersection is not empty and use the some element that I know to be in there to prove that j must equal k. So I'm going to prove the converse of this when I go to prove, or not the converse, the contrapositive, when I go to prove disjointness. Anyway, so just to get started on the first one, take any arbitrary element out of the set 0 to 1. Because we know that these C sub lambdas form a partition over the interval from 0 to 1, then x is in one of the cells of the partition, and therefore if we consider that representative C sub lambda, which we know to be in F, you know, by definition of them sharing a cell in the partition, their difference is a rational number. Notice, moreover, that both of them are taken from the interval from 0 to 1, and therefore the difference is somewhere between -1 and 1. So therefore it's in this intersection, and therefore this number shows up in the enumeration somewhere for some possible choice of k. So let's say that x minus c lambda is r sub k, right? So r sub k is that k, right? That k is the one that gives us this rational number. Well, then just moving c lambda to the other side, you know that x is equal to r sub k plus c sub lambda. C sub lambda is an element of f, and that makes this contained within r sub k plus f. So we proved that, you know, for an arbitrary choice out of this set, I found an element in I found a set in the union such that it's in that set, therefore it's in the union. Okay, proving this step is even easier. We know that every element of f is between 0 and 1. Every r sub k is between -1 and 1. So the least that their sum could be is -1, and the most that it could be is 2. Very easy proof. Okay, disjointness. So I start with the converse, or the contrapositive, which is to say I'm assuming that this is not empty, and so I have some element x in the intersection. Now, by being in both of these, I know that there exist some two elements of f such that x is equal to r sub j plus the first one, and also r sub j plus the second one. Now, right, just put the rationals on one side and the representatives on the other, and you get that this is a rational number. Because these are two elements in the interval from 0 to 1, and their difference is rational, they are in the same cell of the partition. And but also they were chosen from it, right? Like these are two elements of f from our hypothesis. Keep in mind, f has only one representative from each cell. So if these are two representatives of the same cell and they are both in F, then they have to be equal to each other, because F only gets one representative per cell from the construction of F. Now, that means that the indices are equal. That means that these two elements are the same. That, if you go back to here, since the C's are the same, then you can cancel them and get Rj equals Rk. That, because this is an enumeration, so it is a one-to-one function, and therefore tells you that the indices must be equal, and that is what I wanted to show. So my three claims, so to speak, right? This subset, and this equality have all now been proved. Okay, to finish the proof, right, we basically just rehearse what we talked about in the overview, which is that we can now say that the measure of the interval from 0 to 1 is equal to 1 is less than or equal to the union over all of the feathers. Again, that's because we know that the interval 0 to 1 is contained within this union, so that follows by monotonicity. Again, I still need to prove monotonicity. I'll do that in a minute. This is equal to that by countable additivity. We know that the sets are disjoint, so that's a valid move, and the number of feathers is countable because it just has this index, right, this index over the natural numbers. And every one of these is a translation of the same feather, so let's just say that any one of these is equal to the constant C, so we're summing the constant C infinitely many times. And also we know that the measure of this union is less than or equal to the measure of the interval from -1 to 2, which has measure 3. So it's a finite sum. Therefore, C is equal to 0. Therefore, the sum over C is equal to 0, which again is greater than or equal to 1. And that's a contradiction. So all that remains is to tie up that loose end about proving monotonicity for this general length measure M, and then the proof will be complete. Okay, so proof that M is monotonic. It's really, the whole proof is just going to rely on a couple facts, so I won't even need intervals or translation invariance. So in fact, this is kind of interesting because all that matters is that the measure is never negative, and that it's additive. And really, it only needs to be finitely additive for this property to hold. So that's kind of interesting that that's all you need for monotonicity if you have countable additivity. So, suppose that you have A a subset of B, and we'll show that the measure of A is less than or equal to the measure of B. Now, if the measure of B is infinity, then this holds trivially. Otherwise, if the measure of B is finite, then we can, and this is a very important move. I mean, you use this in probability theory, and we will be using this decomposition of a set into disjoint pieces like this, especially under conditions like that. But even in some case, right, we'll find other ways to do decomposition even when this doesn't hold. So anyway, I want to emphasize that this is going to be a really important move. So it might seem like a little set theory hack, but it's actually just a tool of the trade, and we'll use it a whole lot. So anyway, we take B and we decompose it into the A part, because part of it is A, together with all of B that's not A, right? And you can prove that B is equal to this set with, set theory if you want to. It's a very easy proof. It's like super basic proof. So this is just decomposing B into its A part and everything else. Now, apply countable additivity, in particular just to these two sets. Now, if the measure of A were infinity, and this has to be non-negative, then the measure of B would be infinity, but that's contrary to our assumptions. So we can't have that be infinity. We can't have that be infinity by the same logic. So Now we can say, well, look, we know that m is always non-negative no matter what we are talking about, and in particular, I'm going to say that about b minus a, right? So this has to be non-negative because m is always non-negative on any set by assumption, right? And but then from this equation right here, the m of b minus a is the same thing as m of b minus m of a, right? If you just move it to the other side of the equation. So they're equal to each other and it's greater than or equal to 0. So move m of a to the other side of the inequality and the proof is complete.